In nuclear physics, the valley of stability, also called the nuclear valley, energy valley, or beta stability valley, is a characterization of the stability of nuclides to radioactivity based on their binding energy. Nuclides are composed of protons and neutrons. The shape of the valley refers to the profile of binding energy as a function of the numbers of neutrons and protons, with the lowest part of the valley corresponding to the region of most stable nuclei. The line of stable nuclides down the center of the valley of stability is known as the line of beta stability. The sides of the valley correspond to increasing instability to beta decay, beta minus or beta plus. The decay of a nuclide becomes more energetically favorable the further it is from the line of beta stability. The boundaries of the valley correspond to the nuclear drip lines, where nuclides become so unstable they emit single protons as single neutrons. Regions of instability within the valley at high atomic number also include radioactive decay by alpha radiation of spontaneous fission. The shape of the valley is roughly an elongated paraboloid corresponding to the nuclide binding energies as a function of neutron and atomic numbers. The nuclides within the valley of stability encompass the entire table of nuclides. The chart of those nuclides is known as a Segre chart, after the physicist Emilio Segre. The Segre chart may be considered a map of the nuclear valley. The region of proton and neutron combinations outside of the valley of stability is referred to as the sea of instability. Scientists have long searched for long-lived heavy isotopes outside of the valley of stability, hypothesized by Glenn T. Seaborg in the late 1960s. These stable nuclides are theoretically expected to occur at particular, narrow configurations of atomic and neutron numbers, forming what has been called an island of stability outside of the valley of stability. Description: all atomic nuclei are composed of protons and neutrons bound together by the nuclear force. There are 287 different nuclei that occur naturally on Earth, each corresponding to a unique number of protons, called the atomic number, Z, and a unique number of neutrons, called the neutron number, N. The mass number, A, of a nuclide is the sum of atomic and neutron numbers. A equals Z plus N. Not all nuclides are stable. However, according to Byrne, stable nuclides are defined as those having a half-life greater than 1018 years. And there are many combinations of protons and neutrons that form nuclides that are unstable. A common example of an unstable nuclide is carbon-14 that decays by beta decay into nitrogen-14. With a half-life of about 5,730 years. 14. 6C14. 7N plus E minus plus nu. E. In this form of decay, the original element becomes a new chemical element in a process known as nuclear transmutation, and a beta particle and an electron antineutrino are emitted. An essential property of this and all nuclide decays is that the total energy of the decay product is less than that of the original nuclide. The difference between the initial and final nuclide binding energies is carried away by the kinetic energies of the decay products, often the beta particle and its associated neutrino. The concept of the valley of stability is a way of organizing all of the nuclides according to binding energy as a function of neutron and proton numbers. Most stable nuclides have roughly equal numbers of protons and neutrons, so the line for which Z equals N forms a rough initial line defining stable nuclides. The greater the number of protons, the more neutrons are required to stabilize a nuclide. However, some nuclides with larger values for Z require an even larger number of neutrons, N greater than Z, to be stable. The valley of stability is formed by the negative of binding energy, the binding energy being the energy required to break apart the nuclide into its proton and neutron components. The stable nuclides have high binding energy, and these nuclides lie along the bottom of the valley of stability. Nuclides with weaker binding energy have combinations of N and Z that lie off of the line of stability and further up the sides of the valley of stability. Unstable nuclides can be formed in nuclear reactors or supernovas. For example, such nuclides often decay in sequences of reactions called decay chains that take the resulting nuclides sequentially down the slopes of the valley of stability. The sequence of decays take nuclides toward greater binding energies, and the nuclides terminating the chain are stable. The valley of stability provides both a conceptual approach for how to organize the myriad stable and unstable nuclides into a coherent picture and an intuitive way for understanding how and why sequences of radioactive decay occur. The role of neutrons. The protons and neutrons that comprise an atomic nucleus behave almost identically within the nucleus. The approximate symmetry of isospin treats these particles as identical, but in a different quantum state. This symmetry is only approximate, however, and the nuclear force that binds nucleons together is a complicated function depending on nucleon type, spin state, electric charge, momentum, etc., and with contributions from non-central forces. The nuclear force is not a fundamental force of nature, but a consequence of the residual effects of the strong force that surround the nucleons. One consequence of these complications is that although deuterium, a bound state of a proton, P, and a neutron, N, is stable, exotic nuclides such as diproton or dineutron have no stability. The nuclear force is not sufficiently strong to form either pp or nn bound states, or equivalently, the nuclear force does not form a potential well deep enough to bind these identical nucleons. Stable nuclides require approximately equal numbers of protons and neutrons. The stable nuclide carbon-12, 12C, is composed of 6 neutrons and 6 protons. For example, protons have a positive charge. Hence within a nuclide with many protons there are large repulsive forces between protons arising from the Coulomb force, by acting to separate protons from one another. The neutrons within a nuclide play an essential role in stabilizing nuclides. With increasing atomic number, even greater numbers of neutrons are required to obtain stability. The heaviest stable element, lead, Pb, has many more neutrons than protons. The stable nuclide 206 petabits has Z equals 82, and N equals 124. For example, for this reason, the valley of stability does not follow the line Z equals N for A larger than about 40. Z equals 20 is the element calcium. Neutron number increases along the line of beta stability at a faster rate than atomic number. The line of beta stability follows a particular curve of neutron-proton ratio, corresponding to the most stable nuclides on one side of the valley of stability. This ratio is small, corresponding to an excess of protons over neutrons in the nuclides. These nuclides tend to be unstable to beta plus decay, since such decay converts a proton to a neutron. The decay serves to move the nuclides toward a more stable neutron-proton ratio on the other side of the valley of stability. This ratio is large, corresponding to an excess of neutrons over protons in the nuclides. These nuclides tend to be unstable to beta decay, since such decay converts neutrons to protons on this side of the valley of stability. Beta decay also serves to move nuclides toward a more stable neutron-proton ratio. Neutrons, protons and binding energy. The mass of an atomic nucleus is given by m equals Z m p plus n m n minus e b c 2 display style ME equals ZM underscore P plus NM underscore N frac E underscore B C caret 2, where M, P, display style M underscore P, and M, N, display style M underscore N, are the rest mass of a proton and a neutron, respectively, and E, B, display style E underscore B, is the total binding energy of the nucleus. The mass energy equivalence is used here. The binding energy is subtracted from the sum of the proton and neutron masses because the mass of the nucleus is less than that sum. This property, called the mass defect, is necessary for a stable nucleus. Within a nucleus, the nuclides are trapped by a potential well. A semi-empirical mass formula states that the binding energy will take the form E, B, equals A, V, A, minus A, S, A, 2, slash, 3, minus A, C, Z, 2, A, 1, slash, 3, minus A, minus 2, Z, 2, A, plus or minus delta A, Z, display style E underscore B equals A underscore V A underscore S A caret 2/3 A underscore C frac Z caret 2 A caret 1/3 A underscore A frac A 2 Z caret 2 A PM delta A Z closing curly bracket. The difference between the mass of a nucleus and the sum of the masses of the neutrons and protons that comprise it is known as the mass defect. EB is often divided by the mass number to obtain binding energy per nucleon for comparisons of binding energies between nuclides. Each of the terms in this formula has a theoretical basis. The coefficients A, V, display style A underscore V, A, S, display style A underscore S, A, C, display style A underscore C, A, display style A underscore A, and a coefficient that appears in the formula for delta A, Z, display style delta A, Z, closing curly bracket, are determined empirically. The binding energy expression gives a quantitative estimate for the neutron-proton ratio. The energy is a quadratic expression in Z, display style Z, that is minimized when the neutron-proton ratio is n/z, approximately equals 1 plus A, C, 2, A, 2, slash, 3. Display style n z approx 1 plus frac A underscore C 2 A underscore A caret 2/3. This equation for the neutron-proton ratio shows that in stable nuclides the number of neutrons is greater than the number of protons by a factor that scales as A 2 slash 3. Display style A caret 2/3. The figure at right shows the average binding energy per nucleon as a function of atomic mass number along the line of beta stability. That is, along the bottom of the valley of stability. For very small atomic mass number, H, He, Li, binding energy per nucleon is small, and this energy increases rapidly with atomic mass number. Nickel 62, 28 protons, 34 neutrons, has the highest mean binding energy of all nuclides, while iron 56, 26 protons, 30 neutrons, is a close second. These nuclides lie at the very bottom of the valley of stability. From this bottom, the average binding energy per nucleon slowly decreases with increasing atomic mass number. The heavy nuclide 238U is not stable, but is slow to decay with a half-life of 4.5 billion years. It has relatively small binding energy per nucleon. For beta-decay, nuclear reactions have the generic form AZXAZ plus 1x plus E minus plus nu E, where A and Z are the mass number and atomic number of the decaying nucleus, and X and X are the initial and final nuclides, respectively. For beta plus decay, the generic form is AZXAZ minus 1x plus E plus nu E. These reactions correspond to the decay of a neutron to a proton, or the decay of a proton to a neutron, within the nucleus, respectively. These reactions begin on one side or the other of the valley of stability, and the directions of the reactions have to move the initial nuclides down the valley walls towards a region of greater stability, that is, toward greater binding energy. The figure at right shows the average binding energy per nucleon across the valley of stability for nuclides with atomic mass number A equals 125. At the bottom of this curve is tellurium 52T, which is stable. Nuclides to the left of 52T are unstable with an excess of neutrons, while those on the right are unstable with an excess of protons. A nuclide on the left therefore undergoes beta minus decay, which converts a neutron to a proton, hence shifts the nuclide to the right and toward greater stability. A nuclide on the right similarly undergoes beta plus decay, which shifts the nuclide to the left and toward greater stability. Heavy nuclides are susceptible to alpha decay, and these nuclear reactions have the generic form AZXA4Z2X plus 42He. As in beta decay, the decay product X has greater binding energy and it is closer to the middle of the valley of stability. The alpha particle carries away 2 neutrons and 2 protons, leaving a lighter nuclide. Since heavy nuclides have many more neutrons than protons, alpha decay increases a nuclide's neutron-proton ratio. Proton and neutron drip lines, the boundaries of the valley of stability, that is, the upper limits of the valley walls, are the neutron drip line on the neutron-rich side, and the proton drip line on the proton-rich side. The nucleon drip lines are at the extremes of the neutron-proton ratio. At neutron-proton ratios beyond the drip lines, no nuclei can exist. The location of the neutron drip line is not well known for most of the Segre chart, whereas the proton and alpha drip lines have been measured for a wide range of elements. Drip lines are defined for protons, neutrons, and alpha particles, and these all play important roles in nuclear physics. The difference in binding energy between neighboring nuclides increases as the sides of the valley of stability are ascended, and correspondingly the nuclide half-lives decrease, as indicated in the figure above. If one were to add nucleons one at a time to a given nuclide, the process will eventually lead to a newly formed nuclide that is so unstable that it promptly decays by emitting a proton or neutron. Colloquially speaking, the nucleon has leaked or dripped out of the nucleus, hence giving rise to the term drip line. Proton emission is not seen in naturally occurring nuclides. Proton emitters can be produced via nuclear reactions, usually utilizing linear particle accelerators, LINAC, although prompt, i.e., not beta-delayed. Proton emission was observed from an isomer in cobalt-53 as early as 1969. No other proton-emitting states were found until 1981, when the proton radioactive ground states of lutetium-151 and thulium-147 were observed at experiments at the GSI in West Germany. Research in the field flourished after this breakthrough, and to date more than 25 nuclides have been found to exhibit proton emission. The study of proton emission has aided the understanding of nuclear deformation, masses and structure, and it is an example of quantum tunneling. Two examples of nuclides that emit neutrons are beryllium-13 mean life 2.7 times 10^-21 s, and helium 5.7 times 10^-22 s. Since only a neutron is lost in this process, the atom does not gain or lose any protons, and so it does not become an atom of a different element. Instead, the atom will become a new isotope of the original element, such as beryllium-13 becoming beryllium-12 after emitting one of its neutrons. In nuclear engineering, a prompt neutron is a neutron immediately emitted by a nuclear fission event. Prompt neutrons emerge from the fission of an unstable fissionable or fissile heavy nucleus almost instantaneously. Delayed neutron decay can occur within the same context, emitted after beta decay of one of the fission products. Delayed neutron decay can occur at times from a few milliseconds to a few minutes. The U.S. Nuclear Regulatory Commission defines a prompt neutron as a neutron emerging from fission within 10^-14 seconds. Island of stability. The island of stability is a region outside the valley of stability where it is predicted that a set of heavy isotopes with near magic numbers of protons and neutrons will locally reverse the trend of decreasing stability in elements heavier than uranium. The hypothesis for the island of stability is based upon the nuclear shell model, which implies that the atomic nucleus is built up in shells in a manner similar to the structure of the much larger electron shells in atoms. In both cases, shells are just groups of quantum energy levels that are relatively close to each other. Energy levels from quantum states in two different shells will be separated by a relatively large energy gap. So when the number of neutrons and protons completely fills the energy levels of a given shell in the nucleus, the binding energy per nucleon will reach a local maximum, and thus that particular configuration will have a longer lifetime than nearby isotopes that do not possess filled shells. A filled shell would have magic numbers of neutrons and protons. One possible magic number of neutrons for spherical nuclei is 184, and some possible matching proton numbers are 114, 120 and 126. These configurations imply that the most stable spherical isotopes would be FLEROVIUM-298, UNBINILIUM-304 and UNBIHEXIUM-310. Of particular note is 298 FL, which would be doubly magic. Both its proton number of 114 and neutron number of 184 are thought to be magic. This doubly magic configuration is the most likely to have a very long half-life. The next lighter doubly magic spherical nucleus is Lead-208, the heaviest known stable nucleus and most stable heavy metal. Discussion. The valley of stability can be helpful in interpreting and understanding properties of nuclear decay processes such as decay chains and nuclear fission. Radioactive decay often proceeds via a sequence of steps known as a decay chain. For example, 238U decays to 234, which decays to 234 millipascals, and so on, eventually reaching 206 petabits. 238. 92. U. 4.5 times 10 9 y alpha 234 90 th 24 d beta minus 234 m 91 par 1 min beta minus 234 92 u 2.4 times 10 5 y alpha 230 90 th 7.7 times 10 4 y alpha 226 88 Rath 1600 y alpha 222 86 Rn 3.8 d alpha 218 84 po 3 min alpha 214 82 pb 27 min beta minus 214 83 by 20 min beta minus 214 84 po 164 mu s alpha 210 82 pb 22 y beta minus 210 83 by 5 d beta minus 210 84 po 138 d alpha 206 82 pb. Display style begin array L C caret 238 underscore 92 U2 alpha 4.5 times 10 caret 9 C Y underscore 90 caret 234 TH2 beta caret 24 C D underscore 91 caret 234 M par C2 beta caret 1 C min CE caret 234 underscore 92 U2 alpha 2.4 times 10 caret 5 C Y underscore 90 caret 230 TH2 alpha 7.7 times 10 caret 4 C Y CE caret 226 underscore 88 Ra 2 alpha 1600 Y underscore 86 caret 222 RN2 alpha 3.8 C D underscore 84 caret 218 Po 2 alpha 3 C min underscore 82 caret 214 PB2 beta caret 27 C min underscore 83 caret 214 by 2 beta caret 20 C min CE caret 214 underscore 84 Po 2 alpha 164 mu C S underscore 82 caret 210 PB2 beta caret 22 C Y underscore 83 caret 210 by 2 beta caret 5 C D underscore 84 caret 210 Po 2 alpha 138 C D underscore 82 caret 206 PB end array. With each step of this sequence of reactions, energy is released and the decay products move further down the valley of stability towards the line of beta stability. 206 petabits is stable and lies on the line of beta stability. The fission processes that occur within nuclear reactors are accompanied by the release of neutrons that sustain the chain reaction in an intense flux of antineutrinos. Fission occurs when a heavy nuclide such as uranium-235 absorbs a neutron and breaks into lighter components such as barium or krypton with the release of additional neutrons. The heavy nuclide of uranium has a large neutron-proton ratio, since many neutrons are required for its stability. The lighter nuclides from fission therefore have an excess of neutrons, and they are therefore unstable to beta- decays which emit antineutrinos. For the same reason, free neutrons are most often emitted in the fission process, whereas free protons are not. In 1956, Rain and Cowan exploited the anticipated intense flux of antineutrinos from a nuclear reactor in the design of an experiment to detect and confirm the existence of these elusive particles. See also alpha decay, beta decay, gamma decay, neutron emission, proton emission. spontaneous fission, cluster decay, stable nuclide, nuclear shell model, nuclear drip line, neutron-proton ratio, magic number, physics. The live chart of nuclides, IAEA with filter on decay type. The valley of stability. Video. A virtual flight through 3D representation of the nuclide chart. By CEA, France. The nuclear landscape. The variety and abundance of nuclei. Chapter 6 of the book Nucleus. A Trip into the Heart of Matter by McIntosh, Ikalili, Johnson, and Penner describes the valley of stability and its implications. Baltimore, MD. The Johns Hopkins University Press. 2001. ISBN 0-801-86860-2.